All right, this video is going to be a quick video going over how to do one of these styles of limits. What I want you to see is that we're doing the limit as x goes to infinity. I have 3 times x. That piece right there is going to go to 3 times infinity, which is infinity. And then what I want you to see is we also have 10 over x right here. The limit is x goes to infinity of 10 over x. Well, that goes to 0. And then that has me take the sign of that thing. So this entire fraction here goes to 0. So then I take the sign of 0, and that goes to 0, because I know the sign of 0 is 0. So what I want you to see is that fundamentally we're doing the limit as x goes to infinity of infinity times 0. This is one of the indeterminate forms that we talk about in BC. Infinity times 0. And the goal is generally to turn it into a hoppable indeterminate form, which would be either 0 over 0 or infinity over infinity. And we can do either one here, but I think the standard way to do this is to get to a 0 over 0. As a reminder, I can 1 over 3. If I asked you to do, actually I don't want to do 3. I'll do 7. If I asked you to do 1 divided by 1/7, you would copy dot flip, and you would wind up getting 7. I can reverse that type of thing as well. I can take 7 and say that it is 1 over 1 over 7. For example, say that I had, let's go with 6 over 23. 6, if I had 6 times 23, I could write that as 6 times 1 over 1 over 23, which I could also write as 6 over 1 over 23. Long way to say that I can take advantage of this fact of copy dot flip algebra to reverse things like this and make them like that. And that's what I'm going to do right here. If you see this x right here, my goal is to turn it into a 0 over 0 or an infinity over infinity. So basically, I got this thing right here. It is not currently a fraction in this form or this form. By taking advantage of this kind of algebra right here, I can turn this into a fraction. So I'm going to write equals limit as x goes to infinity. I'm going to write my fraction bar. Now I'm going to leave the 3 in the top, and I'm going to leave the sign of 10 over x in the top, and I'm going to 1 over just that piece right there. What's that going to give me? 1 over x in the bottom. Bottom line here is that if I were to copy dot flip this whole fraction, I would get something back that looks exactly like this. So it's totally legitimate to reverse that. Now I've got a large fraction, and what I'm hoping is that one of these two hoppable forms is what I have here. So let's go ahead and check. All right. I have 3 times the sign of 10 over x. I'm letting x go to infinity. 10 over infinity, well, that goes to 0. We just did that. And then the sign of that also goes to 0. So what do I get in the top? I get 0 over. Now let's check to see what we get in the bottom. I get 1 over infinity, because x is going to infinity. And you should know that 1 over infinity, 1 over an infinitely large number, that also goes to 0. So we do indeed have something that goes to 0 over 0. Now, remember, when I get one of these two, then whatever I have becomes hoppable, and we can use Hopital's rule. So I'm going to hop. Oops. When I do that, I still carry my limit notation. And in my top, I'm actually going to save the top for later. Oh, one thing I want to say here. So oftentimes with these, you get a number here. It's a lot easier to leave this number here than it is to move it to the bottom. Some people want to 1 over this whole thing right here. Just leave that number up top, that coefficient, and your life will be a lot easier. So only put the 1 over x in the bottom. So what was I saying? We are going to use Hopital's rule. So I got to derive the top and I got to derive the bottom. I'm going to go ahead and derive the bottom first. That is x to the negative 1. That, if I dir it, is negative 1 times x to the negative 2, which is equal to negative 1 over x squared. So in the bottom, I get negative 1 over x squared. In the top, we have this piece right here. The 3 is definitely going to come along for the ride, so I'm going to write my 3 times. Now, in order to take the derivative of the top, I need to use some chain rule. The derivative of the innards, the derivative of the innards here, I use the same idea as when I took the derivative of this. So the derivative of 10 over x is going to be negative 10 over x squared. And then I'm going to do the derivative of the outer, which is cosine of. And then on the inside, I wind up getting 10 over x. I just keep that the same. Now, what I want you to see here, there are all kinds of things that cancel here. This looks very messy. It does not look any better than this. But if I do some simplification, then all of this kind of zips away. First off, the negatives cancel, so they become positive. Next, the x squareds cancel, so that cancels with that. And this is a multiplication right here, times that positive 10. So what do I wind up getting? I get this, times this, all over the 1. Well, anything over 1 is just itself, so you might say that we don't even have a fraction anymore. This is going to be the limit as x goes to infinity of 3 times a positive 10 times the cosine of 10 over x. And then we can't plug in infinity, but we can do is talk about what happens to this as I let x go to infinity. That's what a limit is. So when we do that, I get 10 over infinity. Well, what's 10 over infinity? Well, that goes to 0. So this goes to 0. And then what do I get? I get 3 times 10 times the cosine of 0. And what do I know the cosine of 0 is? It's 1. So I get 3 times 10 times 1, which gives me 30. And that's how we do one of these problems. So hopefully that makes some sense. Hopefully you can do this with similar problems. And then remember, these are the indeterminate forms from AB. And this right here is one of the many indeterminate forms from BC. And our goal is always to make it hoppable. Hop, simplify. Sometimes we hop a couple times. Anyway, hopefully this helps. See you later.